An Elementary Course in Synthetic Projective Geometry by Derek Norman Lehmer. Chapter 10, On the History of Synthetic Projective Geometry. Section 161, Ancient Results. The theory of synthetic projective geometry, as we have built it up in this course, is less than a century old. This is not to say that many of the theorems and principles involved were not discovered much earlier, but isolated theorems do not make a theory, any more than a pile of bricks makes a building. The materials for our building have been contributed by many different workmen from the days of Euclid down to the present time. Thus, the notion of four harmonic points was familiar to the ancients, who considered it from the metrical point of view as the division of a line internally and externally in the same ratio. The involution of 6 points cut out by any transversal which intersects the sides of a complete quadrilateral was studied by Pappus, but these notions were not made the foundation of any general theory. Taken by themselves, they are of small consequence. It is their relation to other theorems and sets of theorems that gives them their importance. The ancients were doubtless familiar with the theorem, 2 lines determine a point, and 2 points determine a line, but they had no glimpse of the wonderful law of duality, of which this theorem is a simple example. The principle of projection, by which many properties of the conic sections may be inferred from corresponding properties of the circle which forms the base of the cone from which they are cut, a principle so natural to modern mathematicians, seems not to have occurred to the Greeks. The ellipse, the hyperbola, and the parabola were to them entirely different curves, to be treated separately with methods appropriate to each. Thus, the focus of the ellipse was discovered some 500 years before the focus of the parabola. It was not until 1522 that Werner of Nuremberg undertook to demonstrate the properties of the conic section by means of the circle. Section 162, Unifying Principles. In the early years of the 17th century, that wonderful epoch in the history of the world which produced a Galileo, a Kepler, a Tycho Brahe, a Descartes, a Desarg, a Pascal, a Cavalieri, a Wallace, a Fermat, a Huygens, a Bacon, a Napier, and a goodly array of lesser lights, to say nothing of a Rembrandt or of a Shakespeare, there began to appear certain unifying principles connecting the great mass of material dug out by the ancients. Thus, in 1604, the great astronomer, Kepler, introduced the notion that parallel lines should be considered as meeting at an indefinite distance, and that a parabola is at once the limiting case of an ellipse and of a hyperbola. He also attributes to the parabola a blind focus, caicus focus, at infinity on the axis. Section 163, Desargs. In 1639, Desarg, an architect of Lyons, published a little treatise on the conic sections, in which appears the theorem upon which we have founded the theory of 4 harmonic points. Section 25. Desarg, however, does not make use of it for that purpose. 4 harmonic points are for him a special case of 6 points in involution when 2 of the 3 pairs coincide, giving double points. His development of the theory of involution is also different from the purely geometric one which we have adopted, and is based upon the theorem, section 142, that the product of the distances of 2 conjugate points from the center is constant. He also proves the projective character of an involution of points by showing that when 6 lines pass through a point and through 6 points in involution, then any transversal must meet them in 6 points, which are also in involution. Section 164, Poles and Polars. In this little treatise is also contained the theory of poles and polars. The polar line is called a transversal. The harmonic properties of poles and polars are given, but Desarg seems not to have arrived at the metrical properties which result when the infinite elements of the plane are introduced. Thus, he says, when the transversal is at an infinite distance, all is unimaginable. Section 165, Desarg's theorem concerning conics through 4 points. We find in this little book the beautiful theorem concerning a quadrilateral inscribed in a conic section. which is given by his name in section 138. The theorem is not given in terms of a system of conics through 4 points, for Desarg had no conception of any such system. He states the theorem, in effect, as follows. Given a simple quadrilateral inscribed in a conic section, every transversal meets the conic and the 4 sides of the quadrilateral in 6 points, which are in involution. Section 166. Extension of the theory of poles and polars to space. As an illustration of his remarkable powers of generalization, we may note that Desarg extended the notion of poles and polars to space of 3 dimensions for the sphere and for certain other surfaces of the second degree. This is a matter which has not been touched on in this book, but the notion is not difficult to grasp. If we draw through any point P in space a line to cut a sphere in 2 points, A and B, and then construct the 4th harmonic of P with respect to A and B, the locus of this 4th harmonic for various lines through P is a plane called the polar plane of P with respect to the sphere. With this definition and theorem, one can easily find dual relations between points and planes in space, analogous to those between points and lines in a plane. Desarg closes his discussion of this matter with the remark, similar properties may be found for those other solids which are related to the sphere in the same way that the conic section is to the circle. It should not be inferred from this remark, however, that he was acquainted with all the different varieties of surfaces of the second order. The ancients were well acquainted with the surfaces obtained by revolving an ellipse or a parabola about an axis. Even the hyperboloid of 2 sheets contained by revolving the hyperbola around the major axis was known to them, but probably not the hyperboloid of 1 sheet, which results from revolving a hyperbola about the other axis. All the other solids of the second degree were probably unknown until their discovery by Euler. Section 167. Desarg had no conception of the conic section as the locus of intersection of corresponding rays of 2 projective pencils of rays. He seems to have tried to describe the curve by means of a pair of compasses, moving one leg back and forth along a straight line instead of holding it fixed as in drawing a circle. But he does not attempt to define the law of the movement necessary to construct a conic by this means. Section 168. Reception of Desarg's work. Strange to say, Desarg's immortal work was heaped with the most violent abuse and held up to ridicule and scorn. Incredible errors, enormous mistakes, and falsities. Really, it is impossible for anyone who is familiar with the science concerning which he wishes to retail his thoughts to keep from laughing. Such were the comments of the reviewers and critics. Nor were his detractors altogether ignorant and uninstructed men. In spite of the devotion of his pupils, and in spite of the admiration and friendship of men like Descartes, Fermat, Mersenne, and Roberval, his book disappeared so completely that 2 centuries after the date of its publication, when the French geometer Chasles wrote his History of Geometry, there were no means of estimating the value of the work done by Desarg. 6 years later, however, in 1845, Chasles found a manuscript of the Brouillon project made by Desarg's pupil de la Hire. Section 169. Conservatism in Desarg's time. It is not necessary to suppose that this effacement of Desarg's work for 2 centuries was due to the savage attacks of his critics. All this was in accordance with the fashion of the time, and no man escaped bitter denunciation who attempted to improve upon the methods of the ancients. Those were the days when men refused to believe that a heavy body falls at the same rate as a lighter one, even when Galileo made them see it with their own eyes at the foot of the Tower of Pisa. Could they not turn to the exact page and line of Aristotle which declared that the heavier body must fall the faster? I have read Aristotle's writing from end to end many times, wrote a Jesuit provincial to the mathematician and astronomer Christoph Scheiner at Ingolstadt, whose telescope seemed to reveal certain mysterious spots on the sun, and I can assure you that I have nowhere found anything similar to what you describe. Go, my son, and tranquilize yourself. Be assured that what you take for spots on the sun are the faults of your glasses or of your eyes. The dead hand of Aristotle barred the advance in every department of research. Physicians would have nothing to do with Harvey's discovery about the circulation of the blood. Nature is accused of tolerating a vacuum, exclaimed a priest when Pascal began his experiments on the pedidome to show that the column of mercury in a glass tube varied in height with the pressure of the atmosphere. An elementary course in synthetic projective geometry. This book was written by Derek Norman Lehmer, Assistant Professor of Mathematics, University of California. It was published by Ginn and Company, Boston, 1917, and is now in the public domain. The text is available for free download at Project Gutenberg, read by Jim Renholt. Programming and illustrations by Jim Renholt, 2020. Corrections and comments are appreciated. Thank you for listening.